Those of you that don't know me, I'm Dr. Tom Herring. I teach physics at Western Nevada College. I'm also the director of the Jackson Davis Observatory, which is where you are, so you probably have heard the name. And this is part of the usual series of talks, the second and fourth Saturday of every month. We have something. The schedule's right up there. I'll preview a couple of those. You turn the red lights off so we have the usual color here. Tonight's topic, particle physics for everyone. This is a bit of a lofty goal on my part, but I thought I'd give it a shot. We'll see if this really works. So, what are we talking about with particles? Well, it really comes down to this. How small is small? How small is the smallest thing? And that's really what particle physics is attempting to study, is finding the fundamental building blocks of stuff. And I'm going to stop myself at saying stuff. You probably, if you look into this more, you might say the fundamental building blocks of everything. But there's some parts of everything that isn't the stuff that we're talking about here. In fact, it turns out probably most of the universe is not this. That's another talk. We'll get into it a little bit, but you know, we can take, say, some coffee, reduce it down. Anybody recognize this beautiful molecule right here?
Caffeine.
That's caffeine, indeed. And there's a hydrogen out there sticking out on the end. So hydrogen you can blow up and you get a nucleus and an electron, right? What's in the nucleus of a regular plain old hydrogen atom? A proton, right? And even the term atom means kind of the idea behind that word in Greek is the smallest thing, right? Well, it's not. There's structure to an atom, right? Turns out there's also a structure to the proton, and that's where we're headed today. Tonight is what's the structure inside of the proton, and can we break it down even further? If you've been here for some of my other talks, I talked about quantum physics. It gets into the very small. A lot of quantum physics concentrates on these guys, electrons, and how they behave in the presence of these guys and other stuff. Then we had nuclear physics. We talked about what goes on in nuclei of atoms. This is even smaller. What goes on inside the stuff that makes up the nucleus of the atom. And it's pretty weird. We're going to get into these names, but a little preview here. These color guys, these are quarks, and these little bits in between are called gluons, because they stick stuff together. Seriously, that's where it comes from. So how do you look at small stuff? Well, you can't use a microscope after not very small, it turns out. You don't see atoms with a regular microscope. You can see atoms, the structure of atoms with an electron microscope, but that doesn't use visible light, it uses electrons. And back to the quantum physics talk, turns out everything has sort of this wave nature, and you use waves to look at stuff. And you need waves with short enough wavelengths to correspond with the size of things you're looking at. That gets really tough when you start looking at these subatomic fundamental particles, is the colloquial term, these irreducibly small things. It turns out that looking at these, using these shorter wavelengths of any kind of wave corresponds with more energy. So you have to keep kicking, you need much more energy to look at smaller and smaller things. So here's one of the first particle accelerators. This is a model of the very first cyclotron. Anybody heard of a cyclotron? That's cool. They use magnetic fields and electric fields to accelerate particles. It's a little bit hard to see in this picture. See this little line right here in between? It's actually splitting this circle up into two D-shaped things. And they are called Ds because they're like a capital D. And you put a particle with some charge in here, some extra charge on it, positive or negative. Doesn't really matter. And you introduce a magnetic field that points in and out of the page, and you use an alternating electric field, and you get these particles whipping around in circles. Well, that wasn't good enough. It turns out you run up against some limits on how fast you can push a particle with a cyclotron. There's some other things. This is a big Van de Graaff. Anybody know the Van de Graaff generator? You see that in physics class. Stand on a stool, put your hand out, it makes your hair stand up. Have you seen those Van de Graaff generators? I wouldn't touch that one. But, that's a big linear Van de Graaff, and it's really used to accelerate charged particles. That was the original purpose of the Van de Graaff generator. Van de Graaff wasn't looking to make people's hair stand up. He wanted to accelerate electrons, make them go fast, in order to give them a lot of energy and study what they do with small structures. There's a bigger cyclotron. This is about a 1960s something era, 60-inch, that's that diameter there, cyclotron at Berkeley. So this is the evolution of this guy. And they just keep getting bigger and bigger. There's a whole bunch of extra stuff that goes into these, right? All the support material. Then anybody know this one down here?
Yeah, well, the one is CERN.
This one is CERN. This is Fermilab. It actually, it looks like they have, it looks like they're these two rings. It looks like they're the same size. They're not. This one's actually a little bit smaller around, just perspective in the picture. Two different rings. There's CERN in Switzerland, sort of the state of the art when it comes to particle colliders, at least for now. The Chinese are planning to build their own particle collider. And you can see all these different experiments mapped out at CERN, the CMS, ALICE, ATLAS, LHCb. Anybody know the nickname for this particle collider? The Large Hadron Collider. We're going to talk about what hadrons are and why they picked that name. The Large Hadron Collider here. But all these particle accelerators, notice they keep getting bigger. There's actually a bit of a move now to go smaller. There's some interesting tricks involving the wave nature of photons. We think we can build, there's potential to build tabletop sort of things, maybe this size, that would work almost as well as Fermilab as far as accelerating charged particles. The details of that remain shrouded in some very bizarre physics. Essentially, what you do is you try to use an oscillating electric field along with some laser pulses to get things going, to get these particles moving. It's much more of a linear collider, meaning in a straight line instead of these kind of circular colliders like most of these are. Most of these are circular things. You notice that if you look real close at CERN, they have kind of two paths stretched out and they cross every once in a while. They cross when they're going to smash stuff together at the different experiment sites. So you get one set of particles going this way, another set of particles going this way, and then you cross the beams. I know they said don't cross the beams in Ghostbusters, but you do it on purpose here so that you can smash particles together at very, very, very high energies. And some awesome results have come out of that, particularly lately. So why did we do it? Why did we do all this? It started in the 30s, and through about the 60s, people were using particle colliders, not like Fermilab or CERN quite yet, but they started to find all this stuff, lots and lots of particles, and they started to think, well, are these all fundamental particles? They sure look like it. That's not really a particle. I just had to throw in some zoo pictures because of and this was really the term at the time. They said, this is like a zoo. We're finding all these species of particles. They're all over the place. We're hundreds of them. Is it the case that there are hundreds of fundamental particles that make up everything? Boy, that's gonna suck, was the consensus. Because then you got to keep track of hundreds of things, and it sounds really hard. And boy, it would be nice if we could at least try to put them into some categories, right? So there, you can see a whole bunch of these. Anybody recognize some Greek letters in here? You know, physicists have this tendency to use Greek letters. There's a muon right there, a neutrino, the nu for neutrino, capital lambda, lowercase omega, psi. That's my favorite. Anybody know that guy? Anyway, that's psi right there. All of these things started popping up, and they said, well, we've got to find some way to put them into boxes, at least. If we're going to have a hundred and some or hundreds of fundamental particles that make up everything, then we'd better at least be able to categorize them. So they started categorizing, and they said, well, what should we keep track of? To what's important to know about a particle? Now this is stuff we kind of knew from other studies of quantum mechanics and atomic physics. It's nice to know what the charge is, positive, negative, or none, also known as neutral charge, right? So really, two kinds of charge, or you don't have any. You can have positive charge, you can have negative charge, or you just don't have any. Most of the time, this charge for a particle comes in, for these fundamental particles, it pretty much always comes in some increment of a fundamental amount of charge, called they call it the fundamental charge. It's still called the fundamental charge in a lot of physics textbooks, even though it turns out you can break it up into something smaller. So we thought we had fundamental. The name has still stuck around for the past 100 years or so. It's not really all that fundamental, but it's the amount of charge that an electron carries. An electron has negative kind, right? A proton has the same amount of charge that's positive kind. For any of you that know the terms, it's 1.602 and a bit times 10 to the minus 19 coulombs, where a coulomb is a lot of charge. 10 to the minus 19, that's how much an electron has, not very much. Mass is another important thing to keep track of. In particle physics, you'll hear people say, well, that thing has a mass of so many MeV. Well, if you go look up MeV in a physics book, this is a mega electron volt. Mega meaning a million, and electron volt means an amount of energy. How much energy does it take to move an electron through a potential difference of 1 volt? So they're talking about energy here. What they really mean is energy per c squared. How does that work out to be mass? Anybody remember? We've talked about the E equals mc squared, right? So m must be E divided by c squared. And that's what particle physicists are doing all the time. When they say the Higgs boson has an energy of 126 and whatever, GeV, giga electron volts. What they mean, they say it's mass. It has a mass of that much. So no, it has an energy of that much, and then you divide it by c squared and you get mass. But particle physicists, if you want to sound like a particle physicist, when you're at the party and particle physics comes up, which it happens, then you're going to say, oh well, what about that particle with so many MeV of mass? You really mean MeV per c squared, and all the particle physicists know it. So that's how they talk. Another important thing for particles is spin. We talked a little bit about it in quantum physics talk. Who was here for the quantum mechanics history? Spin is this weird thing. If you look it up, even in a lot of physics books, they'll say, oh, it's intrinsic angular momentum. Well, it's only kind of like intrinsic angular momentum. That's the kind of, angular momentum is a quantity of motion associated with things that rotate, right? So if you think of that model of atoms where you have the proton and the electron that rotates around the outside, there's some orbital angular momentum of the electron because it orbits, right? But then they say, oh, well, the electron also spins like the planet Earth spins around its own axis. That intrinsic spin around your own axis. But electrons and all these other particles in the zoo, they're point particles. They don't really spin, they don't really have their own axis. In fact, they're on some level, they're not even a particle. They're a little bundle of energy in a wave. How is it that they can spin? Well, it turns out that mathematically, this thing that we call spin is very much like, almost exactly like, intrinsic angular momentum. So you see it all the time, this comparison to spinning around your own axis to quantum mechanical spin, and that's actually really where the name comes from. Do particles really spin around on their own axis? It works, it's a sure good model, but heck if I know. I don't see them, and probably not is the short answer, because they're really these kind of wavy little collections of energy that probably don't rotate around, but it's a convenient model, and so we use it. And it turns out to be really important for our discussion here, the spin. So we want to keep track of these things. And all of these experiments on all those particles in the zoo, muons and taus and neutrinos and everything, they're trying to determine what's its charge, what's its mass, what's its spin. And those are still important today at all the particle accelerators everywhere. They're smashing stuff together and they find a new thing. That's what they said. Mass, that's usually the first biggest thing you want to find out. Charge, turns out it's relatively easy to figure out if it's positive charge or negative charge, because positive charges moving inside a magnetic field will spiral around in one direction, and negative charges will spiral around in the other direction in the same magnetic field, even a relatively weak one. So it's pretty easy to separate them up. The neutral charges, they don't get deflected by a magnetic field at all. So pretty easy to deal with. We're good at that. Mass, we relate it to energy. We're reasonably good at that. Spin, a little bit trickier to do, but it turns out that spin also interacts with the magnetic field, so we can usually figure out spin. But we have to find the particle first. And having enough energy to make enough mass is the tricky part. And that's why the Higgs boson was so tough to find. It's pretty big. I said mega electron volts here. The Higgs boson is in giga electron volts, billions of electron volts. Thousands of times more than this. So getting there is why we need those bigger and bigger things. So another important thing to keep track of with particles is how do they interact with each other? Well, in physics, an interaction between two things we call a force. Not the force, a force. Okay? Despite my t-shirt today, everybody get the joke? This is momentum right here, the time rate of change of momentum. It's a little physics going on there. These are the forces we know about. We think there are 4 of them in the universe that make up all the other forces that we really talk about. Turns out most of the forces that we experience and talk about, if you come take an introductory physics class, we'll talk about 2 of these 2. We'll talk a little bit about gravitational forces, and we'll mostly talk about things that end up being an electromagnetic force. Friction, air resistance, me pulling on a rope, me pushing on a box. Those are all really ultimately electromagnetic forces. Because they're electrons on the outside of most of the stuff we interact with, right? And electrons have negative charges. Everybody knows what like charges do, right? They'll repel each other. So if my electrons get too close to your electrons feel a push, and you go, hey, don't touch me. And I can say, I'm not. My electrons never came into contact with yours. They just pushed against them from afar. The physicist's excuse. Everybody read the little comic here from XKCD, one of my favorite web comics. It makes it look like we know about gravity. So there's 4 fundamental forces. Gravity, boom, we know that one. This is Newton's description of gravity right here. Turns out this works pretty good for doing things like explaining most of the orbital mechanics of our solar system and landing probes on comets and stuff like that. But it starts to fall apart. It doesn't work so well to describe what happens with galaxies moving around. There's something missing. Something pretty big, it turns out, missing in our gravity. Maxwell's equation, everybody knows Maxwell's equations, right? It describes this stuff, electromagnetic stuff, really, really well. And this is sort of a force, a static electric force. 2 charges will push on each other. The strong nuclear force, well, it's this thing, and it's strong, you know. We actually know quite a bit more about the strong nuclear force, but explaining it in English is rough. Mathematics, sure, we can math the heck out of a strong force. But a good conceptual idea, it really is. It's what holds these a lot of these subatomic particles together. And it holds some of them together better than others. But it's also what holds nuclei together. Think about what's in the nucleus. Say a helium nucleus. It's got 2 protons and 2 neutrons. Those 2 protons are positively charged. What should they do to each other? Push each other apart, right? Well, the strong force is stronger than the electromagnetic force of trying to push them apart, so it wins. And then the weak force, well, something radioactive decay, blah, blah. Fundamental force. We actually know quite a bit about the weak force. And it turns out the electromagnetic and the weak forces are on some level unified. We think they fundamentally come from the same actions in the universe. And at some point in the very, very early universe, like the first billionth of a second, they were the same thing exactly. There was no difference between the two. But they're a little bit different now. Mostly the weak force is responsible for beta decays and some other nuclear processes. But most of what we see day to day are these two. We all experience gravity, right? Turns out, even though this comic makes it looks like we have gravity nailed down, we know beans about this one. We know more about the others than gravity. A lot more. But keeping track of how these particles interact is one of the things that particle physicists try to do. And they interact via these forces. So some interact via the strong force, some via the weak force, some via the electromagnetic force. And we haven't seen any subatomic particles interact via gravity at all, so maybe gravity's something else. We don't know. This is also an important topic for particle physicists. It came up through studies of quantum mechanics. Paul Dirac, anybody remember Paul Adrien Maurice Dirac? English physicist. He came up with a solution to Schrodinger's wave equation that took into account special relativity, or relativistic speeds of things. And he predicted in 1928 that there should be this stuff called antimatter. He didn't call it that, but he said there should be some stuff that has the same mass as all these other things we're talking about, an electron in particular, but it should have the opposite charge. An anti-electron. We call it a positron most of the time. But it has exactly the same amount of mass as an electron. It's just positively charged and negatively charged. If you stick them together like this, you get some gamma ray photons. Each gamma ray photon has an amount of energy exactly equal to the mass of one of these things. So you take the total mass and you split it up into pure energy, and it shoots out as gamma rays. So if we can, there's a lot of energy coming out. If we could do matter and antimatter reactions, we get lots of energy. Gamma rays might be a slightly dangerous source of energy, but hey, it could work out. But pure annihilation is what happens here, meaning all of the mass, all of it, turns into energy. This is not like the nuclear stuff I talked about in my nuclear physics. This is in the nuclear weapons, atomic bombs, tiny bits of mass turn into energy. Here, all of it turns into energy. All of it. So it's a big, big difference. Over here I've got a picture of a regular hydrogen. Here, this is a positive nucleus with a negative electron going around the outside. This here is anti-hydrogen, a negative nucleus with a positron going around the outside. They've made this stuff at CERN and kept it around at least for a little while. See, it's trying to figure out what it does. This positron that was predicted by Dirac in 1928 was found 4 years later, 1932. A guy named Carl Anderson said, yep, positrons exist, found them, here they are. Good job, Dirac. And of course, Dirac, a Nobel laureate for a lot of stuff. But these things produce plenty of energy. Most physicists think that this antimatter, its mass, behaves just like regular mass. We have no reason to suspect otherwise. Meaning that even though this is antimatter, this positively charged thing, its mass will still gravitationally attract other masses. Turns out that has not been experimentally verified, because, well, we don't have a lot of antimatter around. It's probably the most valuable substance on Earth because of its rarity. There's just not much antimatter. And it turns out we go looking elsewhere in the universe and there's just not much antimatter. And we don't know why. Almost all of the matter we see in usual stuff is regular kind of matter. Positive stuff in the middle, negative stuff around the outside. Almost all of it. And how did we end up with this? Well, that's a fundamental question of physics, and nobody has a good answer to date. So, let's talk a little bit about names for this stuff. Don't worry about remembering the details. There will not be a test. I'm not Mike, I'm not a slave driver. I give enough tests. But I found a good quote from Enrico Fermi here. Right? There's hundreds of the things. What? I can remember all that. If you could remember that, you'd be a botanist, right? So, one of the first divisions was actually this division, bosons and fermions. This is out of quantum mechanics. These bosons are things that obey mathematical statistical rules that were derived by a guy named Bose, an Indian physicist, and Einstein. The Bose-Einstein statistics. And it turns out these bosons, they can share quantum states. Remember in the quantum physics talk we said you can only have if you're a quantum particle, if you have a particular mass and energy, and you have a particular spin, that's unique. Nobody else can share that with you. Well, that's only true for fermions. Bosons can share. So if I cool down bosons, they all get in this energy well here. They all get to the same place. They can overlap in quantum state, which makes them pretty weird things. They also, turns out, all these bosons, their spins are integer multiples. They're either 0 or 1 or 2 or 3, etc. And so things with integer spins we call bosons. And we figure they can condense into these states. Anybody heard of a Bose-Einstein condensate? That's what they're talking about. Bosons that have been cooled down to be in the same quantum mechanical state and have a whole collection of them in the same state. Fermions don't do that. This fermions named after that guy. It's actually Paul Dirac that named fermions after Fermi. These fermions, they have one half spins, or 1/2, or maybe 3 halves, or 5 halves, or 7 halves, etc. But half times integers, right? And they can't share states. So once I get a fermion down in this lowest state, I have to have one in the next state up. I can't jam extras in. They don't condense any further than 1 per available quantum state. So we knew about those from quantum mechanics, bosons and fermions. Leptons, we knew about electrons pretty early on. We found them in atoms. These neutrinos up here, the electron-type neutrino, was just proposed and then found much later, but proposed as a way to explain energy deficits in nuclear decays, particularly beta decay. You keep seeing beta decay pop up. Turns out the production of this has to do with that weak force that we talked about briefly. All these leptons interact with stuff in general via the weak interaction. And so far as we know today, these leptons are indeed fundamental particles. They are point-like particles. They don't have any underlying smaller structure. Let's go through them. We've got electrons, muons, and taus. The muon is a funny story. not really funny. Originally, the name muon is short for mu meson. One of these guys. Turns out, not a meson at all. It's a mu lepton. But they just shortened it, and they still call it the muon because of the name stuff. Muons, electrons, tau. And each type of these parts has this neutrino associated with it. The neutrinos, electron type, mu type, tau type. Anybody see a recent last Nobel Prize for Physics last year, 2015? Neutrino flavor flip. The name, we call these different names, these are flavors of neutrinos. An electron flavor, mu flavor, tau flavor. Turns out that neutrinos can change their flavor as they travel through space. They do it. How? But they do it. It's been measured. And it won a Nobel Prize. The how might win another. Work on it, all you guys here for physics. So, we got to some fundamental particles studying these particle accelerator things. But these other guys, the generally called hadrons, the bigger ones. The hadrons are things that interacted, we noted in these particle accelerator experiments, they interacted via the strong force. All the leptons are doing weak force stuff. Hadrons do strong force stuff. And we broke them into two types. It turns out that some hadrons, these baryons, they have half-integer spins, and they act like these fermions. So some hadrons are baryons and fermions with that half-integer spin. Some are mesons. Mesons have the integer spin, like bosons. Confused yet?
Yes.
So was Fermi. Don't feel bad. He said, if I could remember all that stuff, I wouldn't be here. Right? So it gets really jumbled. You can see where physicists were in about 1960 going, crap. I don't want to have to remember all this stuff. It's really hard. I don't want to do this at all. And things got even stranger. Haha, stranger. There was not this kind of strangeness, sorry. Everybody knows Doctor Strange, right? Comic book character. Movies coming out soon, exciting stuff. But the strangeness that was found actually had to do with some reactions, this reaction in particular, and others like it. A couple of famous physicists, anybody heard of Gell-Mann or Nishijima, particle physicists? I'll show you a picture of Gell-Mann here in a minute. They were looking at some of these reactions, this one in particular, but others very much like it. They said, well, these things are hadrons. They're interacting, this is a proton, this is a pi minus, already been previously identified. They said these hadrons, they interact via the strong force, that's why we call them hadrons. And they make these guys. There's a lambda naught and a k naught particle. But these lambda naught and k naught, they're too heavy, they fall apart. They're big, massive, they're relatively massive particles, they're not stable, they don't last long, and they break up into a proton and a pi minus, just what we started with, and a pi plus and a pi minus. All this energy that we put into these guys before we smash them together turns into heavy stuff, but then the heavy stuff falls apart into basically what we started with. What we started with, plus a couple of extra lighter particles. And these guys, the pi plus and the pi minus, this plus and minus indicates charge. What could you say about these? This must be a particle and anti-particle pair, right? They're the same kind of thing, but one has positive charge and one has negative charge. What's probably going to happen to these guys? They may annihilate with each other, right? Turn into energy again. Because they're positive and negative. Opposites attract. But something weird happened here. They said these strong force things, these things that we produced via the strong force, they should decay really fast. And when we say really fast, let me check my notes here and make sure yeah, really fast, like 10 to the minus 23 seconds. That's about 100 billionth of a trillionth of a second. So just like that. But instead, they seem to stick around for about 10 to the minus 10 seconds, which is practically forever for these things. I mean, that's a 1/10 of a billionth of a second. That's like a long time compared to a 100 billionth of a trillion. And so they said, man, that's strange. That was exactly what was said. These are strange particles. So, well, hey, they have strangeness. Problem solved. These things do something weird. We'll give it a name. We'll continue with more. But it turns out this idea of strangeness let us understand arbitrarily this kaon, this k naught, k0 kaon, was chosen to have a strangeness of +1, and this lambda naught had a strangeness of -1. And so strangeness comes in plus or minus 1, pretty much. And that strangeness existed in other similar reactions. But the strangeness was always conserved. They said, we started the proton and the pi minus, they have zero strangeness. They aren't strange at all. But when we smash them together at sufficient energy, we get things that are in fact strange. But the total strangeness in this strong force reaction remains the same. So it started out not strange, and we get two individual strange things, but negative strange and positive strange make not strange at all. And we're going to keep trying, and it turns out they were able to predict other reactions with strangeness. They found other strange particles, and they said, well, this strangeness must be a thing about particles that we need to know. How much strangeness do they have? And they found some other things, bottomness and topness, which we will get to later. Hey, be glad they almost came out to be beautiness and truthness. Not kidding. So there's Gell-Mann, Murray Gell-Mann, and George Zweig. They came up with this idea. They had looked in, Gell-Mann had looked into strangeness, this guy too, and they came up with this idea of quarks. They said, you know all these things, maybe there's something smaller inside of these things. Well, that's what we've been looking for, the smallest. All of these hadrons, we think leptons, we can't break those up anymore. They don't seem to be strange, really. But these, we got all the strangeness and not strangeness and bottomness and topness, what's going on? So they said, well, there's also, we're gonna give these things some name, quarks. The term quark actually comes from this, from Finnegan's Wake, James Joyce. The 3 quarks for mustard. And it's just a silly name. Zweig proposed that they be called, instead of quarks, he wanted to use the name ACE, because it sounded cool. But quark caught on with physicists. ACE wasn't nerdy enough, I don't know. But these guys, they first proposed an up and a down and a strange, because they'd seen this strangeness. And not very long after that, somebody said, well, I found this other kind of stuff called charmness. So if you said there's a strangeness quark, there's a charm quark. So strange and charm. And then we've got top and bottom here. They were very nearly officially called truth and beauty, but that got, they said, you're getting too bizarre, you're getting too weird. Cut it out with strangeness and charm. Let's give them some sensible names. The top quark wasn't officially, it was predicted, but it was not officially found experimentally until Fermilab in 1990 something, 92, something like that. Relatively recently. But it had been predicted for a long time. The search for the top quark was one of the primary reasons that the accelerator at Fermilab was really put together. Now it turns out that these quarks come in these flavors. They said, well, leptons, let's call them flavors. That's where lepton really got their flavor name. Up and down, charm and strange, top and bottom. There are 6 kinds. Except that, remember there's anti-particles of everything. So there's an anti-up and an anti-down and an anti-charm and an anti-strange and an anti-top and an anti-bottom that all count. So there's really 12 of them. But we'll leave it at 6 since it's the antimatter as well. Makes the charts look nicer, I guess. So turns out that these quarks get held together via something called color charge. Google quantum chromodynamics for more information. That's a whole other talk. Quantum chromodynamics is, and it's kind of charge, like we had positive and negative charge. We said positive and negative charges will try and stick together. But they're in this model of quarks developed by these two guys, Nobel Prize. I don't know for that. They developed this model of quarks that build up all these hadrons. So there's red, and green, and blue color charge. And you need red and green and blue to make 0 total color charge. Or, wait for it, anti-red and anti-green and anti-blue. Because there's anti-everything as well, right? So they simplified it quite a bit though. They went from hundreds of these mesons and baryons, the hadrons and collective, and they said it really comes down to these 12 things, 6 plus their antiparticles. It really comes down to 12 things. That's better. And they won a Nobel Prize. So here's how it is. Those baryons that we were talking about, they have 3 quarks in them. Mesons have a quark and an antiquark. Not necessarily a pair, an exact pair. You'll notice this pi plus particle, it has an up quark and an anti-down. The little bar on top of the little line over the letter means anti, that thing. So an anti-down and an up quark. You'll notice all these colors where there's an anti-strange quark. That purple bear right there. S for strange, bar over the top for anti. Anti-strange and a down quark makes that strange kaon that Gelman was looking at before. So, all of a sudden, now we have this model and we can explain all these things. Turns out it's a good model. No one has ever seen a quark all by itself. Not ever. So, are these things really made of quarks? Well, good question. But this model has accurately predicted other particles that have been seen. So we think it must be a good model. Including some of these so-called exotic hadrons. The standard hadrons, mesons and baryons, a quark, antiquark, a couple of them, and then 3 quarks. This quantum chromodynamic stuff, turns out the colors have to add up. You notice I have a red, a blue, and a green in here to make a proton. Up, up, down. Particle physicists will be impressed when you say, yeah, the proton, that's just an up, up, down. You notice I have red, green, and blue. These other colors, these are to represent, there's an anti-yellow and purple, they're to represent the anti-red, green, and blue colors. We didn't know how to make a color that was exactly anti. They looked into, there are all sorts of schemes for this in quantum chromodynamics and making the pictures. Usually it's associated with cyan and yellow and magenta for anti-stuff from the printing world. But it was kind of RGB, and then there was the anti-stuff that was cyan and magenta. But we got to these weird ones. These are relatively new things. They were predicted not very long after, in the late 60s, early 70s. People said, well, if I can have just 2 or just 3, why not 4 or 5? I said, okay, why not? Because we haven't seen any. That's why not. But the tetraquark, 1, 2, 3, 4, tetraquark, it's really a quark and an antiquark and a quark and an antiquark. This was experimentally confirmed by a couple of different groups, a group in Germany, DESI, and some Chinese group. They found these experimentally in 2013. They're pretty new. We know that there's such a thing, and that's about it. And then it turns out they make up all sorts of, imagine all the combinations when you've got these 12 things that you can combine in this way. You could have a strange and an anti-down and an anti-charm and a top, and that would make a tetraquark of some kind, and you'd give it a name. And usually they give it a name with a number now because they started to run, you run out of letters after a while, after a short while. Anybody know, if this is the tetraquark, what do I call one with 5 in it? It's the pentaquark. Recently confirmed, July 2015, they saw this one. Anybody who want to venture a guess where? CERN, in Switzerland. They saw pentaquarks, and confirmed to, you know, they're sure they saw one with a confidence level of 1 in a few million, so that they were wrong, you know. There's a 1 in a 3.5 million chance that there isn't such a thing as this that they think. But you know, so it takes some oomph to get this together. There's considerable debate now amongst particle physicists. As I was researching that, they say, well, maybe some people say, well, this pentaquark, this tetraquark, it's really its own new thing, and it's all. And some people say, no, it's kind of like two mesons that are stuck together in a sort of a molecule like a thing. There's 4 of them. That's what I care about. And they say maybe this pentaquark is really a baryon and a meson that somehow get stuck together temporarily. Because that would be 5, right? Maybe we're overcomplicating things to say we found these exotic hadrons and they exist. And for how long do they exist? Tiny fractions of seconds. Not like you're going to go digging up in your backyard. But they give us some insight into how quarks might behave. These quarks are sticking together via the strong force interaction. And it turns out even stronger than the strong force that we saw in nuclei associated with nuclear physics. Considerably stronger. A lot of the strength that goes into making a quark a baryon, remember, a baryon could be a proton or a neutron. And there's a proton, and up and up and down, there's a neutron, and up and down and a down. They only differ by 1 quark. So they're pretty close. But I start making these things and I stick them together and they stick together in the nucleus too. But it's from the leftover, the strong force that gathers these quarks together, there's some strength left over which sticks the neutron to the proton, or a proton to another proton, or a neutron to another neutron. But it's just residual leftover strong force strength. So we get to this quark model of matter and we say, well, that looks pretty good. We went from hundreds to 12. We'll call that a success. And we put that together with our leptons, those 6, well, 12, because there's anti-everything, right? There's up to 24.
Zoo again.
We're starting to get into the zoo territory again, but at least it's not hundreds, right? And we go, oh, well, maybe that's not so bad. But what about those forces? They interact, right? And some smarty pants named Feynman and a few others come along and say, well, we'd like to describe these forces, which we've previously described as fields. We say there's a vector field of gravitational forces or electromagnetic forces or weak force or strong force. We'd like to describe it in the realm of quantum mechanics. We want to quantize it. So we want to take this thing that's continuous and make it into, well, let's make it particles since we're particle physicists. So let's find these particles that we can name. And it turns out that, yeah, there are particles that mediate forces. There's your way to sound smart when particle physics comes up at the party. Say, yeah, I know about those particles. There are some particles that mediate forces. And so we put them all together into this standard model. There's our quarks, there's our leptons. These are fundamental things. And here's some fundamental gauge bosons. They're called gauge bosons because they gauge forces. There are W's, there are a couple of those, W plus and W minus. There's a Z boson. That mediates things. There's a photon. We use gamma for a photon. That mediates the electric force. This G, not gravity. It's a gluon. So if we look at these gauge forces, this is the strong force. That's the thing that sticks quarks together and nuclei together. When quarks interact, we say they exchange a gluon in order to stick together. When charges interact, plus charge or minus charge, they exchange a photon to interact. When leptons interact, they exchange, oh nuts, Z's or W's for this weak force interaction. So we covered 3 of the fundamentals, right? Strong force, electromagnetic force, weak force. Anyone notice anything missing?
Gravity.
It's not in here. It's not part of this model. Because particle physicists don't have a particle for that. There is a proposal called the graviton. No one's ever seen it. There's absolutely zero evidence that it exists. But it sure, gosh, it would be handy. But you'll notice there is nothing to describe gravity in here. With a possible exception, this guy's new to the standard model. Very new. Extremely new. Anybody know what this one is?
Higgs.
This is the Higgs. He's called a scalar boson. And we're going to talk about the Higgs a bit more in a minute. That's what everybody wants to talk about for particle physics, right? So here's some more about those forces again. Don't worry about too much about the details, but here's gravity. We know beans about it as far as particle physics goes. Grab a what? Yeah, that's what those astrophysicists do. We'll leave it to them. We'd sure like to figure it out. There's this hypothetical graviton. It does. We don't know if it exists or not. But here's the thing. This is why it's going to be tough to figure out. Look at the strength. This is the strength on the scale of quarks or on the scale of protons or neutrons. On the scale of a quark, where the electromagnetic force between 2 quarks would be 1, gravity is 10 to the minus 41. It's vanishingly tiny small. It's super duper small, right? Even on the scale of protons, so if one proton repels another proton via this, the static electric force with a strength of 1, protons would gravitate at 10 to the minus 36. So I like to say gravity is the wimp on the beach of fundamental forces. Gravity gets sand kicked in his face by guys like the strong force and the electromagnetic force. And even the weak force makes fun of gravity, and his name's weak. Right? Look how much stronger the weak force is. 10 to the minus 7. That's 29 orders of magnitude strong. And then we look at the strong force. Remember I said it's kind of split. There's the fundamental strong force, which is really has to do with quarks. It's only on the scale of quarks. Look how strong it is, 60. Much tougher than the electric charge. But even the residual, the leftover, once I bind quarks together, it's still 20 times stronger, fundamental. So we get some insight into fundamental forces from particle physics. It's one of the big things that particle physicists do. Besides looking for what are some new other particles to add to the zoo that are exotic, that I put together with weird combinations of quarks. They figure out exactly how are these things interacting, and everybody secretly looks for the graviton. They won't admit it, but they want to find it bad. Bad. Nobody would admit looking for the graviton. I mean, look how tiny that is. It's going to be crazy. And it turns out that this tiny amount of interaction force is going to be tough to see. That's why you have to have a lot of particles to see gravity happen. You got to have a lot so that 10 to the minus 41 times trillions of trillions of trillions of particles put together to make a person actually gravitates, right? So we get to this we get to these forces, and we associate them again. Let me go back one with these gauge bosons. With the exception of gravity, we don't have a gauge boson for gravity. We'd love to have a graviton, but we don't have a force particle. We haven't quantized gravity, is the way it's usually said. We haven't taken that gravitational field and turned it into a particle representation yet, with any success. Lots of people have tried. Lots and lots of people. No one has met with any success at all. So, the next thing, is this Higgs boson. It's pretty new, right? This is another XKCD, it's pretty funny. These are visualizations of actual data from the Higgs discovery at CERN. And at CERN, what they're really doing is smashing protons together, but with so much energy that the energy turns into mass temporarily. The little tracks you see coming off of here, all of these little tracks, some of these little cones are photons, all these other tracks are some of those other particles from the particle zoo. And right in the middle is something that adds up to the mass of the Higgs and is predicted to fall apart into all this other stuff through our quark model. To say if we can make these kind of quarks, then they'll fall apart into this kind of stuff. But what is this Higgs particle? What does it do? Well, it turns out that there was a question about, and particle physicists arrived at it kind of because of their terms. Remember they talked about mass in terms of energy? They said, well, why isn't it all just energy anyway? If energy and mass are the same thing, it seems like it's advantageous to be just pure energy and not mass at all. In fact, it's statistically more likely. I calculated it. Look here. Right? And I won't show you calculations. I'm not sure I can pull those off the top of my head. But they calculate. It's far more likely that everything should just be energy, but clearly there's mass around. Look around. Plenty of it, right? Well, what happens is, and then some smart guys, including Francois Englert and Peter Higgs, and 4 others, and in the 1960s, they wrote a series of papers, all of them, some in collaboration, some by themselves. And they all basically proposed that there should be this thing. It's a particle. And it's the particle that we're going to associate with this field that permeates the whole universe called the Higgs field. And they call it the Higgs, it ended up being called the Higgs particle and the Higgs field. And it makes stuff have mass. But here's how it works. This is the typical representation. Think of all these people in the crowd as Higgs particles. They're Higgs bosons. And so, if you imagine there's a whole universe and they're roughly evenly spread. You get a crowd of people and you put them in a room and they'll kind of roughly spread out on average. That's what the Higgs particles will do, right? But then you get some other bunch of energy around here that's a well-known bunch of energy. Right? Say Richard Feynman walks into the, right? Peter Higgs comes in and all the physicists go, Peter Higgs. And so what happens is suddenly it's much harder for whomever this famous bundle of energy is to move through the universe because of the presence of this Higgs field. It crowds around this famous particle. My wife said, oh, that's like Leonardo DiCaprio at the Oscars. Yeah, right? You got all the hangers-on that are the Higgs field, and then you got Leo here that comes in, and everyone goes, oh, it's Leo DiCaprio. And it makes it hard for him to get through here. The Higgs field is the crowd, and all the particles with mass are these popular people. The more popular ones have even more mass. And this mass is really, how hindered are these things from moving through the Higgs field that permeates the universe? So there's this kind of invisible crowd everywhere in the universe. And anytime a particle tries to move through it, depending on its popularity, its mass, it'll have a harder time. That's what this is called the Higgs mechanism. How does this Higgs field give things mass? And so this is an explanation of, there's this background all-permeating field called the Higgs field that makes it hard for some things to move and easier for a photon, right through there. Nobody notices. The photon is the small, unpopular kid at the party. No one notices. He can move through the crowd like nothing's there. But something like a pion, has got some, or even a proton's got some, it has a harder time moving through the field. And so things get mass because they're popular, is the short of This Higgs particle was predicted to have a particular range of masses, and it turns out it landed dead center in the middle of the predicted range of masses, which was kind of good and kind of bad. We found one. Dead center, right where we were looking. However, if it had been more one side or the other of that range, it would have told us something about some fundamental bits of the universe. Being dead center tells us, well, not a whole, there is one. That's it, that's it. And thus, this says, hey, we need some more money, $3 more billion, because we want to look for the Higgs more. So, but you found it, right? And they say, well, kinda. We sort of still lost, because we don't really know. We know it's there, but we don't know what it does. Not exactly. Some physicists are now proposing that this is just one of several Higgs-type things. Maybe those scalar bosons in the standard model, maybe there's a Higgs 1 and a Higgs 2 and a Higgs 3, and they all do kind of this in different ways. So, but they found one. It doesn't have any spin, 0 spin. So it has that integer spin. That's what makes it a boson instead of a Higgs fermion. It doesn't have any electric charge, right? It doesn't have any color charge like quarks do. But it's also very unstable, meaning if you make a particle like you do in the LHC like this, it falls apart almost immediately. It doesn't like to stay together. So they're hard to see. That's why we've had to go to such extremes. So the standard model continues to have trouble. It doesn't say, and for several reasons. Turns out that it's not, has yet to be proven. There are some people that think they've done this, but no one agrees with them. It's not even mathematically self-consistent. That's a whole other talk. Anybody heard about group theory? This is some really cool math. You can, if you learn a little bit of group theory, Rubik's cubes get real easy real fast. The group theory class that I took in graduate school we called group therapy. It was pretty rough, but we made it through it. But study some group theory. Try to win $1 million. There's a problem, the Millennium Prize problems, the Clay Mathematics Institute. Anybody heard of these Millennium Prize problems? The Clay Mathematics Institute, they got some money. If you can solve this mathematically self-consistent problem, there's a Yang-Mills existence, there's a bunch of names for it. But if you can show that the standard model could be mathematically self-consistent, you get $1 million. Boom. Good luck. I encourage you to try. I'm going back through my group theory books again, because, you know, $1 million. Why not? It turns out that the original standard model says, and the original description of neutrinos says, well, they don't have any mass. They just carry energy away from some of these reactions, some excess energy. But no, they have a little bit. They have a tiny bit of mass. Turns out it wasn't a huge problem. We've kind of explained this away with some small modifications, this mathematics in the standard model. But we haven't had any really good experiments. There's some really mostly nitpicky, but still outstanding questions about why do neutrinos have mass? Maybe the Higgs will help us explain this. Maybe neutrinos have a little bit because of what the Higgs does to them. You know, this was an original, a few years ago, this was a much more vexing problem. Now that we have Higgs, now that we have a little bit more good experiment, neutrinos are also tricky to look at because they are so tiny and they interact not well with other stuff. So, but it didn't turn out to be a big problem, but it's still sort of an outstanding, a remaining trouble with the standard model. Neutrinos have mass, we're not sure why. Of course, we're only kind of sure why anything has mass now, so the standard model still suffers from that problem generally. And here's a big one. I've talked with some of you guys about dark matter and dark energy, and the response of particle physics is this. The what? Huh? Dark, no darks. We know about stuff. Matter and antimatter. That's our stuff. Dark what? No mention at all. No, the standard model doesn't predict any of that stuff, and we think it makes up something like 95, 96% of the universe. So particle physics is about 4% of what the universe consists of, we guess. Pretty good guess. But standard model doesn't even start to explain this stuff. We have no clue. Well, we have a couple of clues. No good idea about what this is. It turns out there are some things called axions, which we can start to explain with particle physics, which might be dark matter. Dark energy, that one's that. Don't know. Don't know at all. But also, standard model again. No, this is probably the biggest one. No clue about gravity. Haven't quantized gravity. There are some tries. Anybody heard about loop quantum gravity? String theory. All string theory, loop quantum gravity, all that's just trying to make gravity fit with something that's kind of like the standard model. Almost all of the work that's going into how do I explain gravity says the standard model needs to be modified this way, and then you can do it. No one has any experimental evidence that any of that is the case or true or useful, but we're going to keep looking. But that's what's wrong with this stuff. I'll leave you with a commercial for the next few talks. May the 14th, we'll be talking about this kind of stuff. And May the 28th, Mike Thomas is going to talk about this kind of stuff. Any questions or concerns about particles?
As the universe expands, where does the energy come from to create all these Higgs particles that are needed for this expanding field?
That is one of the outstanding questions about how do we continue to create mass. The usual, and I kind of think cheater answer is, well, it was just there to begin with. There's energy in the Big Bang. Good enough. That's kind of a cheater answer, though. And the connection between this particle physics stuff and cosmology is really interesting, and this brings it up. As the universe expands, what happens? Well, maybe that energy becomes more diffuse, and the Higgs field starts to not work so well anymore, and things with mass don't exist, and things with mass can't stay massive. What if that happens? Bad news for us. More of the universe turns into those things the standard model doesn't explain, like dark energy, maybe dark matter. That would be my guess, is that the universe expands and turns into a big collection of dark energy, and we're all gone. And no matter exists anymore, and the universe becomes a tremendously boring place.
The moon just suddenly, poof, disappeared. Would we immediately at that very instant cease to experience its gravitational attraction, or would there be a lag of latitude?
There's considerable debate about something like that. The method by which it disappears is the real debate. If it really just vanishes from the universe without a trace, then how does it immediately communicate through? We think what would happen if something disappears is that its mass turns into energy in the form of a gravitational wave, for which there has been recent evidence. Everybody's aware of black hole merger, gravitational waves found, seen, for sure, detected. And that's that gravitational wave from the black hole merger, that was some of the mass of those two black holes that stuck together turned into the energy of the gravitational wave. Probably what would happen with the moon. The moon's mass, if it's gonna disappear, the moon's mass suddenly goes and turns into energy in the form of a gravitational wave. What would that do to us? Tides would stop, I guess. But how does that gravitational wave affect the Earth? Maybe it pushes us, maybe we just rock up and down in space-time and we see some really, make a good sci-fi story. What happens if you go up and down in space-time a lot? Maybe you see all sorts of weird stuff happening associated with special relativity and general relativity. Maybe time speeds up and slows down, right? The rates of time pass weirdly. could be all sorts of interesting
Yeah, I
things.
think you get into dimensionality and all that as well.
Yeah.
Where did it go?
Yeah, where does it go? Where did it go? But yeah, one of the questions one of the problems in quantizing gravity and making it fit with particle physics is this particle chain. How does the force mediate it? How quickly, when new mass forms, how quickly does all the mass that's already around find out about it? Is it instantaneous? Because that's what Newton's description of gravity calls for. Boom, mass is there, everybody knows. And then Einstein says, now wait a minute, propagating information at faster than the speed of light is bad news, let's not do that. And everybody goes, well, nuts. What happens? Because we think there's extra mass created from energy. Energy that was not gravitating before is now gravitating. Does it continue to gravitate? What happens? Studying gravitational waves is a way that we hope we can figure out what actually is going on. Studying gravitational waves is ultimately an attempt to add to the standard model and explain gravity on that particle-like scale. I like that question though. I'm gonna propose to somebody that I'm gonna talk to my English colleagues. The sci-fi story: the moon disappears, gravitational waves. We'll credit him. So if you see that come out, it's all your fault. Any other questions?
What's this rumor about Mercury and the sun?
Oh yes, pure speculation. No, everybody knows that May 9th, Mercury is going to pass in front of the sun from our point of view, cast a little shadow, right? We'll be here, when I say we, me, Red, a few of the key volunteers here, we're going to be here at the observatory. When the sun comes up, this process will be in progress, right? It will have started. The transit of Mercury across the sun hasn't happened for what, 10-ish years, Red, something like that? Yeah. It's not, you'll probably get a chance to see it again. It happens with some regularity. It's not the Venus transit. You missed that one. Barring huge advances in medical science, you're out of luck. 170-something years from now, we'll see it again. But Mercury transit we'll probably get to see again in a decade-ish or so. We'll see it again. But we will be here. By the time the sun comes up, it will be in progress. We'll be here observing with some of our telescopes. We've got some solar filters so we can look at the sun. Please don't look directly at the sun. It's usually a bad idea. Unfiltered sunlight's bad for your eyes. So, but we'll be here. That's May 9th. We'll be here just before sunrise. I wouldn't show up until the sun's in the sky, at least coming over the mountains. Official sunrise is a little bit early to see this thing, but come and visit us and see what's going on with the transit of Mercury. Big astronomical event, a daytime astronomical event, which can be viewed here at the observatory. Yeah.
Light cannot gravitate, correct?
Light does not gravitate because it doesn't have any mass. It's all energy.
How can it be sucked into a black hole?
But light, so the reason light is affected by black holes is that light, like all these other things, all these other particles, a photon of light, is constrained to move in space-time. It has to move through space-time. Our universe, the dimensions in which our universe exists. Up and down, left and right, in and out, and time. Light has to move through those. And the presence of a lot of mass distorts space-time. Makes a big dip in it. And so the light gets affected because it has to travel in the dip. This is the short way to explain that. But light doesn't exert a gravitational force on masses, but masses distort space-time, which light has to go through. It's kind of like if you think of a trampoline, right? Think of, this is a little bit of a simplification, but trampoline is all of space-time. You put something heavy in the middle, it makes a dent in it. Right? Light has to travel in the fabric of the trampoline, the space-time. And so if there's a dent there, it has to go further to go through the dent. And it gets its path kind of distorted by that dent.
So it goes in and back out.
In and back out, as long as it doesn't go too close to a black hole. Show up for black holes, 28th. and learn about stuff. This is actually a picture I stole from Interstellar. I remember this. I expropriated for the use of science. Yeah, this is super high tech, scientifically pretty accurate as far as we know what a black hole might look like as it accretes matter. This glowy stuff is some stuff falling towards the black hole, and then you can't see anything. But yeah, this is cool stuff. I think Mike's going to talk about this, and where Kip Thorne did with the studio about black holes. We're going to talk about some interesting spacecraft. This is NASA's vision of warp drive. Any other questions? Well, I hope you stick around. Is the weather looking good out there?
The weather's good and we're beginning to see the stars.
Yeah, there's something to see. So stick around and look through a telescope, and I will hopefully see some of you May the 14th, or maybe even just next Saturday, if it's not too far. Thank you.
Thank you.